Welcome to Flink Forward Asia 2024.
So here's for wrap up the day, ladies and gentlemen. Here's for the last. It's on query layer for stream processing system that will be presenting by Duo. Mr. Parvan as co-founder Platformatory.io and Mr. Avinas as platform engineer Platformatory.io. Please join me in welcoming Mr. Pavan and Mr. Avinas! Yay, yay, yay!
Hello. Hello, everybody. So, great to be presenting at Flink Forward. I'm also standing in the way of 30 people getting back home today, so we will try and wrap up on time. So, it's difficult doing dual talks. Who's operating the slides? Avinash is. All right. Now I am. Okay, all right. Today's discussion. How many of you use Flink? Okay. How many of you use any analytical database? Okay. Okay. How many of you do real-time processing? Anybody here? Of any nature, not just Flink. Okay. Okay. So today's talk is going to have what I think used to be one of the more interesting features in Flink up till 1.16. But let's get into it, right? So introductions. My name is Pavan. I'm on the right. Most of my time is spent at Platformatory, and my day job involves working with customers, but also fiddling with distributed systems. On the other hand, we have Avinash. You want to introduce yourself?
Sure. Yeah, I work as a platform engineer with Platformatory, where I, like I mentioned, we help customers adopt some of these open source technologies such as Flink, Kafka, amongst others. And yeah, I also run a few communities back home in India. So we both from India, where I run a few communities around the same technologies such as Flink, Kafka. So it's so great to see you all here, the Indonesian community, and glad to be here and to present.
Yeah, and thanks to Alibaba for organizing Flink Forward out here. All right. So I think there are three parts to today's talk. The first is a little bit of an architecture backstory on why this would make sense. The second, expect Avinash to get into a show and tell demo, as well as walk you through some Flink internals. And the third part is a bit of a conclusion. There's a little bit of a surprise in the end, but we will talk about that as well. All right. So the world is divided, right? So there are, two broad classes of data. You have operational data. We say this data lives in boxes. Specifically, it lives in boxes like databases of various kinds. It could be SQL, NoSQL, so on and so forth. And you have on the other side big data, right? So big data on the other side lives in buckets, lives in not just S3 buckets. It could live in HDFS. It could live, anywhere else on the cloud, which is a classic quote-unquote big data system. But as it happens today, there is a lot of rate of change of data, as we say it, right? So data is not static. In other words, it's streams of consciousness. Each time you make a transaction, or each time, the grab car or whatever that you use out here makes a turn, all of this generates data, right? So that data not only has to live in operational systems, but it also has to make it to analytical systems. And that's kind of where you have a lot of plumbing in between. And that plumbing is usually streaming systems like Kafka. In other words, the domain of real-time processing that we're talking about, it could be Kafka streams, it could be Flink, or any other stream processing systems. actually work on and operate on data in motion, which is really the data exchange layer between operational systems and analytical systems. The question is, if stream processing systems are in between these operational systems and analytical systems, can you strictly classify them as operational in nature or analytical in nature, right? So that's one of the sort of tougher questions to answer. The answer is it's a little bit of both, right? And therefore, you have to kind of consider a lot of ideas specifically on streaming systems and building streaming systems, right? So they are not quite message brokers, they're not quite databases and stream processing systems, which actually act upon this data in motion, are a slightly different beast altogether. To get a better sense, there's a bit of book reading for those of you who are inclined to reading books that I would recommend. This is actually by, there's my mic drop moment. Okay. There's actually a very good book that I would recommend by Ralph DeBushman and Hubert Dulé. This is specifically about streaming databases. It introduces the idea of what is called, the streaming data plane, which is basically about, where is streaming, right? In terms of where exactly is that data? And specifically in terms of a data domain, what are the challenges specifically associated with data that is in motion? But without much ado, let's move on. I think the core premise behind this talk is that stream processing systems basically apply processing rules on data as and when it comes, right? So in strictly sort of processing terms, stream processing is more about data that is going to come in the future, rather than enacting queries against data that is already out there somewhere. Okay, and this is a very important assumption. But stream processing systems do actually buffer up and manage quite a large amount of state, depending on what kind of operations you perform. So let's suppose you want to perform an operation like, what is the average number of orders over the last 1 hour bucketed into 5-minute windows, right? So that would basically mean stream processing systems will actually have to store that state and basically serve up the answer to that question. The first 5 minutes, it was so many orders. The next 5 minutes, it was so many orders, so on and so forth till the end of the hour. So that brings up the question, what if you could query that state directly in whichever system the stream processing engine such as Flink stores that data, right? And not surprisingly, that's not an unheard of or a novel pattern. For those who are familiar with Kafka Streams actually does this, right? It has a very nifty and very interesting feature that makes systems like Kafka Streams straddle both the operational world as well as the analytical world. So it can be used in both these domains. And the way it broadly works is very simple. In Kafka, the unit of parallelism is basically a partition. In a partition, everything is totally ordered, right? So the way in which Kafka Streams processes Kafka topics is also unsurprisingly by partition. So one of the things that you can do is you can ask a Kafka Streams application, interactively, what the state of a given aggregation is. So the way you do that is by making a metadata call, understanding which partition is hashed to which Kafka Streams application, and then after that, basically you can run interactive queries. I don't mean SQL queries, I mean this is an RPC on each of these streaming applications to get a result straight out of the state store. The question today is more specifically about Flink, right? We're here at Flink Forward, so naturally we're talking about Flink. The first question that I'll also probably turn to Avinash to answer is, why should we do this in Flink? Why is it important? And also show you how do you achieve this in Flink. So Avinash, maybe, why is this important to do in Flink?
Right. See, most of you all are here at Flink Forward. Everybody is here at Flink Forward. So Flink is one of the most widely adopted stream processing system amongst other frameworks that are out there. But primarily that is because Flink supports both batches and stream. I think we've seen this in all of the previous talks. But just to recap on why Flink and why not something else, right? So you have Flink has a unified processing layer which allows you to do both streaming and batches, and has checkpointing and watermarks so that you can save your progress as the stream processing occurs, and has dedicated application mode that you can run along with your application, and has a complete framework for your managing your resources. All of these reasons compel to use something like Flink, and is also one of the most adopted Apache projects as well. If you look at where Apache Kafka was about 5 years ago, that's where Flink is now. Kafka is almost considered as the de facto standard for streaming. So you would be compelled to think of Flink as one of the de facto standards for stream processing, given the adoption that it has seen. And we've seen that in all of the talks that we've seen so far about how Flink is being used at various organizations, and some of the things that you can do with Flink, such as connectors. It's all out of the box with Flink. Yeah. So let's talk about how do you actually query the state store in Flink. So we saw earlier that with Kafka Streams you can go talk to the Kafka Streams application, understand where the state is, and go query it. So that's somewhat similar that we're doing here with Flink. There are three major parts here. One of them is the queryable state client, which is the client that you use to go query the state for. That is, if you're looking for a state for a particular key, you define a queryable state client that will query the task managers. So as you all know, there's every Flink cluster has a whole bunch of task managers and one or more job managers. The queryable state client proxy is another component that is in the task manager, which is responsible for interfacing with the queryable state client, which will ask for or query for a state. And there's the queryable state server, which is responsible for actually serving up those state from the actual state backend. The state backend can either be the embedded RocksDB or the hash map state backend. Those are the two types of state backends that Flink support. But let's talk about how does this actually happen in practice. That is, you have a queryable state client which will talk to any of the task manager. You can actually load balances across the various task managers that you have, and it makes a request to the queryable state client proxy, which then talks to the job manager to understand where a particular key is. Because it's a distributed system, any of the task managers can be processing the key that we're interested in. So the job manager does the bookkeeping of where the particular key, where the particular state is for a key. And using that information, the queryable state client talks to the respective queryable state server. It can either be the same task manager or it can be another task manager, and then fetches the state from the actual state backend. With that, I'll probably demonstrate this so that there's a better idea of what we're looking at.
And demo is worth 1,000 slides.
Yes. Yeah. For the premise of the demo, I have built something simple with Docker Compose. I'll first bring up the environment, and then we can maybe look through what is actually part of the environment. I have a simple setup where there's a broker, Kafka broker, that is going to be our source and also sink. I have a single broker setup. So now first I'm bringing up the Kafka broker, the Flink job manager, and the task manager. And next I have a simple producer, a Python producer that produces, that produces some voltage data. In the Flink job, we are trying to compute the average voltage for a particular household. So you can think of it as the voltage consumed in any household. We are trying to calculate the average and the minimum maximum voltage. And there's a Python script that produces that data for us. And next up, we'll actually go submit the job to the job manager. So I have a container that does that. I'll briefly show you what is happening under the hood with these containers. Now that we have the job submitted, we'll actually take a look at the job ID. We'll need the job ID to actually go query the state store. And there's also a REST or a HTTP interface that we written to actually go query the state store. The state store client, the state store client that we saw earlier is a simple Java library. It's a Java dependency that you would use to query. But in order to make it have a better interface, we've written a HTTP layer on top of it so that you can query by a particular key. That's something that is custom built, but you can use any Java client to actually go query the state. Next up, I'll need to actually update my configuration with the new job ID. And now I'll actually bring up the query client, which is a simple Java application that goes and queries the state store. So this particular Java application has a HTTP interface, so I can query the state by the ID. I think something broke. Live demos are always risky and that. Okay, not sure what exactly broke. But the idea is we should be able to go query the state store. We'll take a look at the implementation and then we'll maybe see if we can get that working once again. But in the job that we've defined a key process function that does the processing, where we've actually initialized a state descriptor which will represent our state. And the state that we're storing is a tuple of 4 values. We're storing a few double values and an integer value, which represents the voltage and the minimum, maximum, and the count of the voltage in a particular window. And the primary configuration that we're looking at here for the querying the state store is to be able to set the descriptor as queryable. So this is something that we'll need to explicitly set a state store to be queryable and give it a name. We'll use this name to actually go query the state store in our client. Rest of it is what one would do in any Flink job. We have the process function where we're actually computing the average and the minimum maximum. So this is not something out of the ordinary. And next we will take a look at how we're actually querying the state store. This is the part where we're actually querying the state store. We need to first initialize a state query client and point it to the task manager host and port. So there's a special server that runs on the task manager which will listen for these state query requests and serve up the response, which is actually the state client proxy that we saw earlier. So we're pointing our client to that particular host and port, which is our task manager's host. And we're setting, we're actually querying the state store using get kv state and using the same name of the state store that we defined earlier. And also the job ID. We need to define what job are we querying the state for, which is the reason why I actually replaced the job ID once I submitted it in our Docker configuration. And the rest of it is pretty standard. The get kv state function actually returns a completable future, which is then going to result in our state, and we get the value of the state. You can probably take a quick look on what's wrong. Yeah, I think the ID did not update. Let me just quickly update this and bring this back up. You need to update the job ID with the latest ID. I think that did not happen. And now if I can bring up the query client. Okay, now Docker Compose failed. Okay, yeah, I think live demo was a bad idea. Yeah, in the interest of time, I'll go back to some of the internal implementation and yeah. So we just looked at how do we query the state store with one of the examples that we had. But there's actually more than one way that you can do it. There are a couple of options on how do you actually query the state store. That is, to be able to make a state store queryable, there are a couple of options. One is the one that we saw, which is on the right, where you set the state store, the state descriptor to be queryable, and you give it a name. Using that name, we can then query the state store. The other option is you mark there's a convenience object that allows you to mark any keyed stream as queryable state, and then you can use that convenience object to then query the state store. Let's once again look at the configuration about how do you actually query it on the client side. We saw this function earlier, the getKV state function, where you pass in the job ID, the name of the state store, and the key that you want to query, and also the information about the actual state store. What are the serializers, how is the state stored within the state store. And it returns a completable future, which is going to eventually return the state, and you can access the value from that particular state. But there are a couple of gotchas that one would want to consider before you think about implementing this. One of them is that the state store the queryable state store does not really allow you to modify the state. Rather, it is read-only. That is, you only query the state store for the values that are already in the state store, and not you cannot go and update any values in the state store, which is what one would want to do as well. You would want to do read-only operations. And if you are using the hash map backend state, there's a catch with the implementation where the state is queried without any synchronization or copying, which means there's concurrency issues that could affect your state. So you would want to be careful of that. But this is not the case with the embedded RocksDB state, where you can safely query the state store without having any concurrency issues. But all of this was great, but we would also want to look at whether it scales. What are the scaling knobs for implementing this at scale? Because you typically run Flink jobs at a lot of scale where there's a lot of state involved. If you end up querying the state, will it actually be an issue for your Flink job? How do you actually scale your query layer as well, so that you have reliable queries? Because if you have any business logic that is depending on querying the state store, you would want that to be reliable and scalable as well. There are 4 primary tuning knobs. One of them, there are 2 on the server side, 2 on the client side. You can set the number of network threads on the server side to listen for the number of requests that you are expecting. You can increase the number of threads as you expect more requests coming in, and also increase the number of query threads, which actually does the querying under the hood on the server, which is going to actually go talk to the state store backend and query. You can increase the number of threads that does that as well. And similarly, on the client side, you have the number or more on the client proxy side, which is still on the task manager. You can set the number of network threads that are actually going to listen for requests, and the number of query threads that are actually going to execute those requests. So all of these are independently scalable, making it a robust system.
Yeah, so who uses this pattern? I think just in our own experience, we've put this into use with IoT customers who process basically gigabytes of data across thousands of devices. A more popular example is from Flink Forward 2022. This is from New Relic specifically, where interactive state stores on Flink are being used to power the golden metric buffer system. So in other words, Flink is being used here as a Redis-like look-aside cache, but at a much lower cost footprint. Basically because you're querying state directly out of Flink as opposed to syncing the output to some output port like Redis. So in other words, queryable state is very interesting, but unfortunately, queryable state is going away, starting Flink 1.18. There are multiple reasons for this, and reasons probably strong enough to warrant a talk about a feature that is actually going away. But let's cover those briefly, right? So I think there are, just to paraphrase the Flink maintainer Yuan on the Flink mailing thread, you should actually read up about this. There are many reasons why queryable state is going away. The first is the query service can become unavailable, especially if you're doing a failover or a transition. Secondly, there are many problems related to rollbacks and checkpoint maintenance. So if a previous rollback needs to be basically done, then the state needs to be rolled back as well. So third reason, and just for point number 2, there are many associated sort of technical reasons specifically about the complexity of the read model. We'll not go into the details, but broadly, those are the reasons. Thirdly, there are a whole host of problems around multi-threaded reads. And fourthly, just being able to do query analysis is not very conducive in this architecture. And lastly, the life cycle of queryable state is tied to the life cycle of the job manager. So therefore, to use it as any kind of ad hoc query system doesn't really work in practice. Which brings us to the conclusion of this talk. There are many interesting things happening in Flink. Queryable state is probably one of them, but the larger evolution of Flink, one should read up about Flip 423. This is an umbrella flip covering a lot of different concerns on how a more evolved modern Flink architecture could look like. But broadly, it will revolve around disaggregated state maintenance. That means the state that used to be local in nature would basically now get continuously uploaded to object storage like S3. That would basically allow for independent compaction, data cleanup, but also ability to share checkpoints between operators and hopefully a new generation of queryable state as well. So there are more questions than answers, but this is an interesting question on what queryable state has to offer in terms of the future. I know this was a slightly advanced talk and a live demo to go with it, but thank you all for being here. Happy to take any questions. And by the way, you can also find this demo, you can run it yourself, just not on a live environment, on github.com, Platformatory, Flink Queryable State Store. Thank you very much.
Thank you.
All right, thank you so much, Mr. Pavan, and also Mr. Afinas from platformatory.io. Please.